All right, so if we think about an action potential, like I'm not going to keep going over this, depolarized, repolarized, hyperpolarized, we are dependent on the movement of those ions. And so now that you have seen this information about the ions in the muscle as well as the nerve, do you see how this is now clinically significant? Why? Okay, so if we can measure the nerve activity, if we can measure muscle activity, and if it's all based on these ions, the ions inside the cell, the ions outside the cell, if someone, I don't know, let's say for example, one of the things that tends to happen is there's usually a shortage of, not shortage, usually potassium could be off, calcium could be off, sodium could be off, in like lab work, okay? So, you know, one of the things that happens with a IV, for example, what is in the IV?
Sodium, salt water, sodium.
Our sodium chloride. Does that ring any bells yet?
Especially when the electrolytes electrolytes are imbalanced, it goes to electrolyte falls off that affects the muscles, including the heart. It also can affect the brain, the nervous system.
Yes. When these ions, the sodium, the potassium, the calcium, they're the big players, okay? But those are not the only ones, okay? We have stuff such as magnesium, zinc, all these other ions, but the big players are my sodium, my potassium, my calcium, and my chlorine. When they are out of balance in the body, some type of physical anomaly is showing up, okay? It could be the heartbeat, okay? It could be muscle reacting or not reacting. It could be nerve reacting or not reacting. So, having the proper balance of the ions is going to ensure that they are functioning correctly. I mean, would you want to be, because of a ion imbalance in your body, constantly having the muscle twitches or something? It can happen. Okay? So it's a good thing that this is what I'm trying to get you guys to understand, is that these are important. Okay? This is all clinically significant. So, in addition to looking at muscle fiber, oh no, did I do something? I did something. There we go. When we're looking at the action potential, because it is now nerve fibers, and we are going to have this hyperpolarization, we're going to see that the stimuli can have a range. It can be from weak to strong. It can be sustained or not, okay? But the nerves are busy pretty much 24/7, 365, 366 if it's a leap year. So, when we talk about the action potentials or the properties of the nerve, these action potentials are hopefully going to have points in time that we can either have another potential get started or we're not. So we're going to say that these neurons, the action potentials, they're sensitive. And their sensitivity for this action potential, okay, basically the stimulus coming in. The stimulus, as long as it is not so strong, like severing of a limb, okay, as long as that stimulus is coming in, there should be a point where that nerve, that particular nerve, needs to recover and go back to rest before the potential starts again. So we're going to say that the neurons have their absolute refractory period or their relative refractory period. So if we look at our chart, and minus 70, that's our resting membrane potential. The resting membrane potential, before that nerve will carry out the action potential, has to reach threshold, roughly minus 55. Okay? Now, the absolute refractory period, how much of the reaction time, okay, how much of that is being used up while the nerve conducts the action potential? Look at the colors. Is it a huge amount, little amount, most of it, not all of it?
Most of it.
The absolute takes up the majority of the action potential time. So that tells me during that time frame, that nerve, that one nerve, is now insensitive to another stimulus. It lasts almost the entire time of the action potential, no matter how large. A second one should not be able to get produced. That's what I was saying. For it to be continuous, it has to be a pain so severe, chances are you're knocked out from the pain, such as severing of a limb. Under most circumstances, okay, pain, that one, but now we're only talking about one nerve. So you can have 10 million others still passing their potential. So you're not going to lose pain. You know what I'm saying? So hopefully during that absolute, we can't start another one. If we do, we're going to suffer some consequences, okay? Because we have to make sure that the cell that it's reaching, is it going to a muscle, is it going to a nerve, is it going to a gland, that it can recover. We need the nerve to recover. So hopefully during this time frame, we cannot get started another potential. Now, once that action potential is almost over, hopefully going into recovery, the stimulus that is strong enough is not going to allow that nerve to recover completely. It's going to continue firing, and it's going to most likely be very painful. That is our relative refractory time. So the stimuli can change. It's not something that's just uniform across the board. Stimuli can be weak, it can be strong, it can be to the point that, yes, you are going to pretty much pass out. How did I end up sleeping every single one? I don't know. But that's very nice.
You only got 40 in it.
Alright, and then I want to get this. So, this we kind of know right now, alright? When we begin to get an action potential and we get to the trigger zone, don't forget, we're going to have transmission of an action potential in both the central nervous system and my peripheral. Okay? So, peripheral nervous system are all of these spinal nerves that exit the vertebra. What type do they consider this to be? Do they consider this to be myelinated or unmyelinated? Or these nerves making up my peripheral exiting the vertebra? These are myelinated because these that are exiting out of the vertebra and moving around to all these areas on the periphery of my body, that's the only protection they have. So they are protected by myelin laid down by the Schwann cell. You guys remember that? All right. Now, in my central nervous system, my brain and my spinal cord, what do I find? Myelinated or unmyelinated? I got both. Because to the outer portion of my spinal cord, myelin, to the inner, unmyelinated, and my brain, to the inner, myelinated, to the outer, un. I got both. But technically, in my central nervous system, where it is unmyelinated, it still has myelin, it's just that thick acute oligodendrocyte coming out and wrapping around stuff. It's not an individual cell that takes this entire nerve, which might be this long, and have an individual cell, the Schwann cell, lay down wrapping. Does that make sense? So, we do say that we have myelinated and un. In my peripheral system, it's myelinated. Now, we kind of mentioned that it would seem like if it is an unmyelinated nerve, that the conduction of that impulse would travel quickly. But it's not. If myelin is present, that transmission of that signal moves quick because the myelin insulates the nerve. Okay? So, if we have an axon that is unmyelinated, think about brain, spinal cord. Okay? We're going to find unmyelinated, the transmission is actually slow. And that unmyelinated axon, what we're going to see happen is, once again, we're looking at passing that potential down the axon, and it does it in an increment. Is everybody with me? Okay? So, once again, let's look at what's happening. My action potential will get started. And if I do it in increments here, notice I've made the inside positive, outside negative. Now